So today we're going to do a review of the GoWise PS1007 1000 watt pure sine wave inverter. Picked this up off of Amazon. Going to do a couple measurements on it. Got the old oscilloscope out. We'll look at the waveform and just check it out under modest load. So a little bit heavier in my old 700 watt square wave inverter that I was testing previously. Bright green plastic front and back cap. Feels like aluminum case with a heat sink. We can see here is a ground lug for attaching to earth ground. In fact, in the instruction book that came with this, it said this should be tied to ground. Now, in a mobile application, car or truck, or even marine, I'm not sure what you would tie it to. Probably the vehicle chassis. But since this is destined for a solar off-grid power installation, we will most likely be tying that to keep things safe, and in code be tying that to a ground rod. So one measurement we're going to check when we're running this thing is to see that if it's make sure that the ground lug is actually connected to that, and then whether or not we're going to measure whether or not this is floating neutral, or if the neutral and ground are bonded together. So that's an unknown. No one was able to answer that question in the product section on Amazon, the Amazon listing. So we'll see. So this comes without any cables whatsoever. So I have a set of 4-gauge cable will hook up. Now I'm not going to pull anywhere near 1,000 or 2,000 watts in the testing, so this cable will be sufficient. If I really was going to be doing closer to rated loads, I would probably use number 2 copper to connect up to the storage battery. But I think for the purposes of our testing for right now, since we're not going to be throwing a huge load on it, the gauge of this cable should be sufficient. So now I have it hooked up to the battery. Made sure our polarities were correct. And notice I don't have a fuse or a circuit breaker in line just yet. When I am in final or close to final installation, I'll be running this probably through a 60 amp circuit breaker, just based on the size of the wiring. And again, it's because of the capacity of that battery. It's only a 55 amp hour battery. I don't think I'm going to get the full 1,000 watts out of this. To do that, I would probably need a 100 amp hour battery, which I don't currently have yet. But again, this is for purposes of testing. So we're hooked up to the battery. I don't have the remote switch hooked up. This did come with the remote switch. So let's see what happens. And system normal. Okay. So here we have a battery level meter. Almost all the lights are on, not lit all the way. The battery was fully charged before I hooked things up. We have no output yet. We have nothing, of course, hooked up to it. So first thing, let's try hooking up our receptacle tester. And if all goes well, if it's all okay, we should have one light on the tester. Okay. So we have the left and the 2 right lights on. And if we look on here, that is correct. That's a problem with this Harbor Freight receptacle tester that I bought. Can't tell what the silkscreen is supposed to be, but we did get the correct light pattern using this receptacle tester because I can't find my other one. So I got this for like $6. Can't beat the price, except the silk screening on that could be better. Okay, so now let's throw initially a modest load. We have a 60 watt light bulb, but when I put it on a kilowatt, it said it was only 55 watts. So let's plug that in, and yay, we have 120 volts. No indication on the bar graph here because it's, 55, 60 watts compared to a 1,000 watt inverter. So here we are getting, so obviously, and the light output looks good. I managed to blow the breaker. Probably caused an arc when I was unplugging it. So we'll put that off to the side. Now what I like to do is I get the scope output on it, and one way to hook the scope up is to just put the probe on some bare wires on a sewer side cable, but rather than do that, I built this little interface box to hook up to the scope. So all we have to do is plug it in, grab the other end here, plug it in, and let's see what happens when we go to scope it. And we have a sine wave. Pattern looks a little wonky. I could see some squaring of the waves in there. I'm getting some strobing effect in on the video. So let's change the time base, and we can see there's a bit of I'll go back and take some measurements on here and report on them in the video, but that does appear to be approximately 60 hertz waveform. Not as clean as I thought. We can see again we're getting a little bit of stepping right in here. Well, let's see what happens when we start putting a load on this. I'll pause the video and be back in a minute. Okay, we hooked the voltmeter up, and this is no load output. We have 116.2 volts out, AC RMS, and 59.94 hertz. So 59.9495, close enough to 60 hertz. And again, looking on here, if you count this 5 milliseconds per division, if you look at the zero crossing, we go back at about 16 milliseconds. That corresponds roughly to 60 hertz. Again, I just wish it was a little cleaner, but compared to the previous inverter, which was completely square wave, this is much nicer. We are looking at, I'm on a by 10 probe with 1 volt per division. So if we look at that, I'm going to say that's close enough. So yes, we do have, which corresponds to the 116 volts. That's about 160 volts peak to peak. Which translates to an RMS voltage of about 116 that we're seeing. It's kind of hard to see all the lines and focus in on them here on the scope on the camera. So far so good. Again, this is with no load. So first thing, let's switch in our light bulb. And we can see no change on that. Although we did get a voltage reduction that's reflected on here. So if we go back to the scope again, the waveform looks more or less the same. There may have been a bit of a slight reduction. So down 114 volts. So let's plug in some additional load on our AC side here. So I'm plugging in a set of Christmas lights. That's adding about 180 additional watts. And our voltage here is dropped to about 111. And we are showing some load on the inverter now. And again, still a pretty good looking sine wave. So now I'm going to add a slightly inductive load. A fan with about, takes about 35-40 watts. And what I can say is our fan is definitely running a lot better than on the square wave inverter. Was not noisy, surprisingly, on the square wave inverter, but it was running slower. So it's running at about the speed that it runs at when it's plugged into the wall outlet. So it's definitely enjoying the better 60 hertz output. So now I'm going to add about 250 watts more with this plug. I have a set of spotlights that we're going to plug in. So we've added another 260 watts of load. It's really supposed to be 300, but the kilowatt said otherwise. So we're doing well here. Still have a nice looking sinusoidal waveform. If anything, I would say it's cleaned up some. So it definitely looks cleaner. What happens when we switch all that load off? Yeah, it gets a little dirtier when there's no load. So actually likes it with a better load, which is good to see. And our voltage went to 113, so again we have fairly decent voltage regulation. Again, I'm going to switch everything off. So 116. Everything's quiet. I don't have my infrared thermometer with me, so I can't comment or I can't give an official measurement, but this is not hot at all. In fact, I don't even hear any fans running on this inverter. It's quiet. Of course, no extra heat in these cables. So I'm already liking this over my old square wave inverter. Now I'm going to pause the video here to disconnect the voltmeter so we can take some current measurements. So I'll be right back. Okay, so now we're going to go back to take another voltage measurement here. So if we go again, hot to neutral, again we're showing our 114.8 volts. And if I go neutral to ground, I'm showing 0. So that's indicating to me this is not floating neutral. Again, much better than my other inverter, which was floating neutral, which meant that there's being voltage carried on both the hot and on the neutral sides, which means that for an AC circuit, if you flip off the switch, there's still power on the other side of that circuit. So if you're screwing in a light bulb, plugging something in, and touch the connector, you can still get burned because typical AC circuit only disables the hot side, expecting only the hot side to be carrying voltage. But with floating neutral, there's actually voltage on the neutral side. So this is telling me that the neutral and ground are bonded. Once everything's powered off, I will take some resistance measurements to kind of verify that. But yeah, this is already a much better inverter than the other one. So anyway, sorry for the crudeness of the YouTube video here and the excess camera movements and all that. I don't quite have a polished operation here. This is actually the first time I'm doing a review of an inverter like this. So I'm going to switch my loads off here. I can see I'm having my batteries already starting to run down. There we go. Now this voltage is coming back. This is an old used battery, by the way. You can see by the dates from 2018, and it's 2022, and I'm making this video. So You can tell there's some age on that, and I don't know how well it's going to hold up under load. So I don't have the full story put together yet on actually why I'm doing this. I have an outbuilding that will be much too expensive to run AC wiring to, so I'm going to do an off-grid solar for this outbuilding. And it's mostly to run some tool chargers, a fan, and some lighting. So we expect the overall load in that building not to really go over about 700 watts to run all of that. Actually, the biggest power consumptive device will be the Cobalt 80 volt battery charger, which can draw upwards of 600 amps. So between that and a fan that I'm going to run in the summertime just to keep cool while I'm in there, maybe a laptop charger, and I've got this built-in USB here so to charge cell phones and or whatnot. Again, not really expecting to power a whole lot out of that, but I wanted a good sine wave inverter so I could run some of the electronics like the tool charger, the laptop charger. Certainly the fan is a lot happier seeing AC. So I have one more load I want to throw on this. So I'm going to go pause the video for another second here. Bear with me while I go get the big load, and let's see what happens. Heat gun. So it's a load, all right. Again, my other Harbor Freight find here for putting shrink wrap, not shrink wrap, heat shrink tubing on cables and whatnot. This is 1500 watts. Let's see from the rating on there, but on the low setting it's about 750 watts. Again, under the 1000 watts of rating of the inverter, but it'll probably represent probably the max load I'll have in the outbuilding, and I have no doubts at this point that the inverter could run this. I'm more concerned about my battery. So let's see what happens when I go on the 750 watt setting here. If all the lights go dark, you know what happened. Well, it's actually working, and I'm getting a low battery alarm, unfortunately. So my battery is having a hard time doing it. The AC went down to 109, 110 volts, and even with the low alarm, we still have reasonable AC waveform there, sine waveform there. So let me turn that off, and we can see where the battery voltage has come back. I should do one last voltage meeting to hook the voltmeter up to the battery and see what happens there. I should grab a second voltmeter actually. So anyway, so zero load, kind of a little messy looking waveform there, but certainly when we go to kill our battery, we get a good waveform on that. So all right, I'm going to stop torturing my battery there and disconnect this thing. Be interesting to see what my amp load is. I might torture the battery one more time. I'm going to hook the go back to the ammeter mode. So let's go back and pause. Okay, first things first. I hooked the voltmeter up to the battery, and we're running about 12.5 volts. So let's throw the old heat gun on over here and see what happens. Yeah, so we can see our battery voltage is dropping. So it starts to complain about below 10.8 volts there, which is about right. But you can see we're coming back up. So I think we're hitting a limit on how many amps my battery can put out. So let me disconnect these clips here. Go to current mode. We'll clamp on there, and looks like we're drawing about 5 amps at idle here. Seems kind of high. And now it's going down by 3 amps. So let's go flip our thing on here. We're exceeding the 60 amp rating. So let's go to the 600 amp rating. Oh yeah, 72 amps. No wonder we're getting a low voltage alarm. I don't think this poor battery can do 72 amp draw, that's for sure. So, all right, so far so good. So let's just go back one more time and take one last reading here. I should probably have paused the video so I don't electrocute myself while moving cables around here. Okay. And we're showing our 59 hertz, 59.94. So let's see what happens when we. So we're holding. Frequency is holding stable. I'm rather happy with this. So I'm going to disconnect the Harbor Freight heat gun. I'm going to think about what I need to do in case my tool charger really does need to pull the full 600 watts. I guess turn off the fan and any extra lights. It also tells me at that 700 watt load that the proposed 60 amp circuit breaker I was going to put in that line would trip. So anyway, let's throw my my 500 watt load back on. Actually, let's do it's and we're holding frequency really well, and that cleans up nicely. So one thing I did notice while doing all the plugging and unplugging here, if you look at this real close, you can see the receptacle looks like a standard ground fault outlet, and does not seem to like a whole lot of strain on it from the plugs. So I would be careful about that when this is out in the field, about how things are plugged in. I'm going to have this mounted on a board, and I'll probably have the cable when it comes off with a strain relief, and attached to the surface, and then I'm going to take my AC out and run that through. Get another level of protection with another additional circuit breaker as I go into my AC distribution for the building. So that'll help keep some of the strain off of that. And I'm not sure what this red light is that comes on every now and then. You may have noticed I did hook up my earth ground here during measurements. I figured may as well be safe. And again, when I go to the official installation with maybe a newer and better battery, I will have a circuit breaker in line here, and I probably will end up going to heavier gauge cables now that I could see what happened with a 750 watt load. So all in all, I'm rather pleased with this. Let's see how well it holds up over time. So again, some of the key points: nice sinusoidal waveform that even when I threw 750 watt load with a straining battery, it maintained near 60 hertz sinusoid. Again, sinusoid is a little messy with no load, but again, it was happy with the load. It was fairly stable voltage output. It is quiet. I put all that load, and I've still yet to hear any cooling fans. It's still cool to the touch. Again, I wish I had my infrared thermometer. Not too happy about the way this outlet flexes with these heavy cables on it. That might be a weak point. This might break with repeated plugging and unplugging. So we'll see again how that holds up over time. Again, no floating neutral, which is in my book much safer for anything AC that's plugged in, because there's no voltage being carried on the neutral side. So when you flip off the light switch, there really is no voltage present at the light socket, or at least there shouldn't be. I have a much higher level of confidence with that. So with that, I think this is a good product. Let's see how it holds up in the field and in the outbuilding over in the summer over time. So thanks for watching my first YouTube video on the review of the GoWise 1000 watt PS 1007 inverter. Thank you.